What's good, guys? Welcome back to the channel, and in this video I'm basically going to be explaining Anomaly and going over the architecture, the components that went into it, how I built it, explaining it in detail. I'm going to try to make this video as concise as possible, but I will still make sure to explain properly. So without wasting much time, let's get into the video. Alright, so basically, Anomaly stands for Financial Anomaly. It is a real-time fraud detection machine learning system that flags fraudulent transactions in real time. So this is especially useful in financial applications, financial institutions, Cash App, Money Point, etc., where they have a huge inflow of transactions and cash moving in and out. So this is where this kind of project can be used. And in case you need it on your resume, this is actually a problem it solves. So the big picture, so it's basically for Money Point, any financial institution, to be honest, where millions of people send money to each other every second. So some of those transactions are fraud. Some of them are used to launder money through a web of fake accounts. So this is to catch the bad transactions in real time before the money disappears. So Anomaly scores how suspicious a transaction looks using two different AI models working together. So before we go forward, you know that the tech stack I used was Python for the language, specifically version 3.14, and Fast API as the framework. So the architecture for Anomaly, it's a pipeline, a conveyor belt that the transactions flow through. So the transaction happens, it goes to the producer, which writes it to Kafka. Kafka is a message queue for ordering the messages so that they are attended to one at a time and there is not an overload. Then the producer writes it to the consumer. This reads it from Kafka and runs our two AI models, which we trained, Autoencoder and GNN. Autoencoder, what does it do? It asks the question, does this transaction look weird? Then GNN works as a person or a model asking the question, do these people rather belong to a criminal network? So basically from this we can see that Autoencoders is looking at transactions as a single entity, one after the other, while GNN works on them as an interconnected web, a network of transactions. Then it combines the scores. If suspicious enough, it publishes the alert to Kafka. Then from our Fast API dashboard, we can let humans check what was flagged. So this is a term-by-term architecture breakdown. Kafka, as I said before, it's a message queue, like waiting in line at a bank. Transactions are placed on the queue and the consumer picks them up one by one. This lets the system handle millions of transactions without crashing. We use Redpanda, which is a faster, simpler version of Kafka. No extra zookeeper software needed. The producer, this is a program that takes the raw transactions and places them onto the Kafka queue. Think of it as the cashier taking customers and giving them a ticket number. The consumer, this is the program that reads transactions from the Kafka queue and actually does the fraud checking. So it's the bank teller calling next and processing the customer. So the queue basically works as a first in, first out, FIFO. So the first entity on the line gets attended to or gets checked before the next. Redis is a super fast in-memory database. We use it to store pre-computed risk profiles for 9 million user accounts. So the consumer can look them up in microseconds. It's like a cheat sheet pinned to a wall, instant access. So basically we are going through 9 million records. So we already have Redis as a backup to enable searching or indexing to be faster. Fast API. This is the Python web framework that gives us a website or API. Humans or other programs can use it to submit a transaction to be checked, look up a user's risk score, and see why a transaction was flagged and check if the system is healthy. So Docker Compose, this is the tool that starts all the infrastructure, the Kafka / Redpanda, the Redis at once in an isolated container. So now that it's out of the way, you understand the architecture, everything that was used, let us explain the two AI models that are being used to flag transactions and check if they are fraudulent. So the two AI models, Y2, the first model is the autoencoder. This is used for point anomaly detection. What it does, it looks at one transaction in isolation and asks, is this transaction individually weird? So how it works, we train the model training. We show the autoencoder millions of normal transactions only. It learns to compress a transaction's features into a tiny summary, and this is the bottleneck, and then reconstruct the original transaction from that summary. So, think of it as a student who reads a paragraph, summarizes it in 3 words, and then tries to write the paragraph again. If the student is well trained, their reconstruction will be very close to the original. So basically, it's compressing what it knows about the transactions into a summary and then tries to reconstruct it from that summary. So the more we train it for that, the more it gets better at that task. So number 2, detection. When a new transaction comes in, the autoencoder tries to reconstruct it. If the reconstruction is terrible, that's high error, it means the transaction contains patterns the autoencoder has never seen before, which indicates anomaly. The threshold, we set a cutoff at the 95th percentile of reconstruction errors on the validation set. This means the top 5% weirdest looking transactions get flagged. So this threshold was calculated as 0.016641 MSE. So now the input features, we want to go over the input features. So first we have the log amount. The log amount is the transaction amount, log transform, because $1 million versus $10 is not a linear difference. Hour of the day, what hour the transaction happened. Fraud often happens at 3 a.m. based on the data set we have from PaySim. Type encoder, the type of transaction, transfer, payment, cash out as a number. The delta balance origin, this is how much the sender's balance changed. The delta balance destination, how much the receiver's balance changed. The error balance origin, mismatch in sender's balance before or after. So this is the fraud indicator. And error balance destination, mismatch in receiver's balance before or after. So then plus 4 one-hot columns for TX type. It breaks the transfer, payment, cash out, debit into separate yes or no columns. So the architecture is 11 to 64 to 32 to 8 to 32 to 64 to 11. So this is basically an asymmetric funnel. It squishes 11 features down to just 8 numbers. This is the bottleneck, the essence of a normal transaction, and then expands back to 11. So that's all for the first model, autoencoders. Now for the second model, which is GraphSage. So now for the second model, which is GraphSage. This stands for Graph, Sample, and Aggregate. So GraphSage basically for structural anomaly detection. So what it does, it looks at the network of people and asks, are these people connected in a suspicious way? How it works, the graph, we build a giant network where each person or account is a node. At each transaction between 2 people is an edge. So this line connecting dots. This gives us 9 million nodes and 12.7 million edges. That's from the interconnected web of accounts. Then GraphSage, this is a type of graph neural network. So for each node, it looks at the node's neighbors and aggregates their information. It does this for 2 layers. Layer 1, tell me about your immediate friends, and then layer 2, tell me about your friends' friends. So after 2 layers, each node has a 64-dimensional embedding. This is a mathematical fingerprint that captures not just the node's own behavior, but the behavior of its entire neighborhood, the accounts that surround it in that web. The fraud rings. Criminals often operate in rings, so account A sends to B, B sends to C, C sends back to A, moving money in circles to launder it. We injected 50 synthetic fraud rings into our training data so that GNN learns what these circular patterns look like. Each ring has 5 to 10 accounts with dense circular transactions. So the risk head, there's a small neural network that takes the embeddings of the sender and the receiver of a transaction, concatenates them, and puts a fraud risk score. This is what the consumer actually uses, not the raw GNN output. So why we don't feed user IDs into the autoencoder with 6 million unique account names, turning them into numbers creates meaningless noise. So why should like user 582 be greater than user 123 matter? So the autoencoder only sees transaction features, not who is involved. The GNN handles the who. So how they work: the consumer, when a transaction arrives at Kafka, the consumer does this in parallel. The autoencoder branch, this extracts the 11 features of the transaction, feeds them through the autoencoder, calculate the MSE, that's the mean squared error between the original and the reconstructed, converts to a 0-1 score, that's 1 minus the EXP minus MSE divided by the threshold. So a higher MSE equals a higher score. The GNN branch, this looks up the sender's embedding in Redis in microseconds, looks up the receiver's embedding in Redis microseconds, and feeds both embeddings through the risk head. So you get a 0 to 1 fraud probability from a sigmoid. So you combine the final score, which is 0.5 multiplied by the AE score plus 0.5 multiplied by the GNN score. So if the final score is greater or equals to 0.5, it's flagged as a fraud and published to fraud alerts Kafka topic. So next, the evaluation metrics. Explained simply, we have the ROC AUC. This is the receiver operating characteristic. Area under curve. Imagine you have 100 transactions, 10 are fraud, 90 are normal. You score each one from 0 to 1. 0 is definitely normal and 1 stands for definitely fraud. Now sort them by score, highest first. A perfect model puts all 10 fraud at the top. A useless model makes them randomly. So ROC AUC measures if I randomly pick 1 fraud and 1 normal transaction, what's the probability the model gives the fraud a higher score. So 1 is perfect, 0.5 is a coin flip. It's no better than random guessing. And then our autoencoder 0.951, this is the score that we got. It's excellent because it almost always ranks fraud higher, which, to be fair, is what we want from a machine learning model. Our GNN 0.652, it's modest on its own node level, but the edge level risk head achieves a 0.9986, which is nearly perfect. So the second evaluation metric we use is PRAUC. This stands for Precision Recall AUC, area under curve. The similar idea, but focuses on how the model identifies the positive, that's the fraud class specifically. This is more useful when fraud is rare, so imbalanced data or 0.1% of transactions are fraud, and 99.9% are normal. So the recall, this has a true positive rate of all the fraud that actually happened. What fraction did we catch? So this is what it does. This is what the metric is evaluating. So if 100 fraud transactions happen and we catch 90, the recall percent is 90%. Our autoencoder 77.8%. It misses about 1 in 5 fraud transactions, which is decent, is good. Our GNN 99.65%. It catches virtually everything. Then the combined score is 99.76%, which catches even more than the GNN alone. So precision, the precision metric of everything we flagged as fraud, what fraction was actually fraud. So if we flag 100 transactions and 60 are real fraud, our precision is 60%. So our autoencoder scored a 91.95%. So when it flags something, it's usually right. Our GNN 51.88%, which means we have a lot of false alarms. And combined 55.84%, more false alarms, but we catch more fraud. Then for our next metric, F1 score, this is the harmonic mean of precision and recall, a single number that balances both. It punishes extreme imbalance. So if you have 99% recall but 1% precision, the F1 score will be very, very low. So our ablation study, it is when we remove one component at a time to prove it is actually useful. So this were the numbers we got for the recall precision F1. So the conclusion from this whole table of data is that the combined systems recall 99.76% is strictly higher than either model alone. The autoencoder catches the weird transactions, the GNN misses, and the GNN catches the network fraud that the autoencoder misses. So they're complementary, and that's really the whole thesis of this project. So now I am going to be explaining key terms used for this project and then the data pipeline. So to show how data flows through the application before we touch on the API endpoints for the fast API application. So now the key terms, we have log transformation. So this is financial amounts range from $1 to $1 million. Raw numbers cause the neural network to focus on only big transactions and compresses the range. So now through this, small and large transactions are treated more equally. One hot encoding, this converts categories, so that's the transfer, payment, etc., into separate yes or no columns. Transfer becomes 1000, payment becomes 0100. The MSE, that's the mean squared error. This is the average predicted minus actual squared. This measures how badly the autoencoder failed to reconstruct the input. Sigmoid, this is a function that squishes any number into the 0 to 1 range, perfect for converting a raw neural network output into a probability. BCE with logits loss, this is a binary cross entropy with logits. So this is the standard loss function for is this a fraud or not classification. It penalizes the wrong prediction. The POS weight parameter tells it fraud is rare, so penalize missing fraud more than false alarms. Node embeddings, this is a 64 number vector that mathematically represents a user's identity in the network. Users who transact similarly and with similar people will have similar embeddings. It is like a fingerprint generated for behavior patterns. Edge index, in PyTorch geometric, a graph is represented as two arrays, sender IDs and receiver IDs. Position 0 of both arrays defines the first edge. This is how we tell the GNN account A sent money to account B. Full batch training, instead of processing the graph in small chunks, which requires special libraries we couldn't install due to using Python 3.14, we load the entire 9 million node graph into memory and process it all at once. This takes approximately 2 seconds per epoch, but works without extra dependencies. Latency benchmark. This is a test that measures how fast does the system respond. We measured both in process scoring speed and the full Kafka pipeline latency. Stratified split. When dividing data into train, evaluation, and test, we ensure that each split has the same proportion of fraud cases. Without this, you might accidentally put all fraud in the test set and the model never learns what fraud actually looks like. PaySim, this is the dataset that simulates the mobile money transactions. It has 6.3 million transactions with realistic patterns. We use it because actual fintech data is confidential, so this is the best we can get our hands on. In degree, out degree, so this is how many transactions flow into a node in degree and out of the node, out of degree. So money muling, this is when criminals recruit real people, often unwittingly, to receive stolen funds in their accounts and forward them elsewhere. This creates a distinctive network pattern that GNN can detect. So now for the data pipeline, how data flows, the PaySim CSV dataset, it goes to prepare data.py. So this file cleans our data, engineers 11 features, scales the features, maps 6 million unique accounts to integer node IDs for GNN, splits it into normal, that's the train, evaluation, and the test dataset, saves to xtrain.pt, xval.pt, xtest.pt, ytest.pt, and testmeta.parquet. Build graph.py, this file, it builds the graph, the 9 million nodes and the 12.7 million edges, computes per node features, injects 50 synthetic fraud rings, and saves graph.pt. So the train autoencoder.py file, this is the file that trains the autoencoder on normal only xtrain. It learns what normal looks like and computes the anomaly threshold. So this saves it to aemodel.pt and anomaly threshold.json. The train gnn.py file, this trains GraphSage on the full graph. It learns the node embeddings that capture network structure and saves it to gnn-model.pt, node embeddings.pt. Then the train riskhead.py file trains a small MLP on sender embeddings and receiver embeddings pairs, learns to predict is this edge transaction between fraud nodes, then saves the riskhead.pt. The cache embeddings.py, this pushes all 9 million embeddings to Redis and gives it a key, and then this takes approximately 203 seconds to load everything. So now for the test and evaluation scripts, we have the model metrics.py. This measures the autoencoder, all the recall precision F1 on the test set. The latency benchmark, it measures speed in process scoring and full Kafka pipeline. Then the ablation study disproves the dual model design by scoring tests with AE only, GNN only, and combined. And right here we can see the key results for each of the files and what they actually did. So yeah. Okay, so now for the endpoints, we have 4 endpoints we tested via curl against a live server. The predict endpoint, this scores a transaction synchronously via autoencoder plus GNN Redis, returns the fraud probability, the AE score, GNN score is flagged, transaction ID, and also publishes it to the Kafka queue. We have the get user ID risk endpoint. This looks up GNN embedding, returns the risk band, embedding norm risk score, and qualitative cluster risk message. We have the get explain transaction ID. So this is the centerpiece. This returns triggered by the autoencoder or the GNN, both or none, with a human readable explanation listing specific reasons. So specific reasons why a transaction was flagged. So reconstruction error z-score versus normal population, large amount detection, balance inconsistency checks, unusual R detection, that's AE that does that, embedding norm outliers, isolated nodes, and self transfers, GNN, that's looking at the network web. And then we finally have the health. This is for the liveness check to make sure your server is running. So now I'm going to be starting up the project to test these endpoints. So first, activate our virtual environment, and then orb stack, that's my Docker. Then we boot up infrastructure. You can just follow the steps in the README and then you can get up to speed. Okay, then we start up the UVCon server. And then we go to this URL once it's done, so we can see it's up and running. Alright, so these are the endpoints. We have the predict endpoint. This scores a single transaction in real time. It runs the autoencoder and the GNN and returns the blended fraud probability. It also publishes it to the Kafka topic for the streaming consumer pipeline. We have user risk, returns a user's GNN based risk profile. So based on the web of accounts and people that we know, it returns a risk profile. It looks up the user's pre-computed graph sage embedding in Redis and reports their risk band. Then we have the explain. So this explains why a transaction was flagged or why it wasn't. It looks up the stored score and produces a human readable explanation of which model branch contributed most to the decision and why. And then this is the liveness check branch. So let's just test this out. And so we see it's healthy, 200 status code, so it's okay. Then let's start with, so we want to run a fraud where the sender basically drains their account, but the receiver never actually gets that amount of money. So this is just a classic scam. So transfer, it's a classic scam. Let's run that, and we can see it's flagged true, the fraud probability is 0.999. The AE score is very high for that. So now we want to run a test for a massive wire fraud of $1.27 million. So both models should fire. So you can see both models fire. The AE score is very, very high. The GNN score is at the 1. So it shows that yes, this is actually a ring of interconnected accounts that work together to do this. So now let us check the risk profile of this user that was engaged in this wire fraud of over $1 million. So we want to check what is this risk profile. So go here. Then we can see their risk band is in the medium. The message, the cluster risk is a moderate structural risk, some proximity to anomalous nodes. So yeah. So now let us use the explain endpoint. We will take the transaction ID that we got from here. I think this was the one of over $1.2 million. So we take this transaction ID and then we come down all the way here. We wanted to explain, okay, why was this flagged? So you can see right here, it says both the autoencoder model and the GNN model flagged it true. Why? The reconstruction is 251.8 times the standard deviations above the normal mean. It's a highly anomalous amount or balance pattern. It's a large transaction amount, $1.2 million. Receiver balance inconsistency. He received $1.2 million, but the balance only changed by nothing, 0. So, and the transaction was at an unusual hour. So the GNN identifies this transaction as a very high risk transaction. So that's basically the end of this video. To just give a quick recap, a quick summary, why does this project matter? You might be thinking to yourself, okay, why does this project matter? Yes, it can be used in fintech companies, but why should this matter on my resume? It's because it has real world scale. You are processing over 6.3 million transactions for 9 million accounts. So it's not a toy data set. If this was applied in a real world setting, it has a dual model architecture. So you're combining point anomaly, that's autoencoder, and the graph-based detection GNN, which is how real fintech companies actually work. You have a production pipeline, so Kafka, Q, Redis, Docker, and the REST API. And then it handles the hard problems, the cardinality IDs, reconstructing from the fingerprint, from the embeddings. So now, in one full summary, the architecture was a full pipeline. Kafka, which is Redpanda, the producer, the consumer, Redis, Fast API, and Docker Compose. The autoencoder, it learns how normal transactions look and flags anomalies by reconstruction error. Graph Sage GNN, this builds a node transaction graph and learns to detect fraud using neighborhood aggregation. So how they combine? They combine together in the consumer with the Redis cached embeddings, and then the metrics ROC AUC, we've already covered all of that, the ablation study, and then So that's basically it. If you found this video helpful, be sure to like and subscribe for more content, as it will help the channel a lot. And I'll see you all in the next video.